Okay, this is analysis of algorithm. My name is Yanofsky. We're up to chapter 32, string matching. Okay, and so let's tell you what it's about. You do a string matching algorithm, or the computer does a string matching algorithm, every single time you press Control F. Okay, what you want is you type in what you want. You have a giant text. Okay, and you want to find a certain pattern in it, and that works. Okay, so you want to find what you're looking for in that pattern. This shows up all over. Okay, word processing, obviously, the World Wide Web. Every time you press Control F, Google, most richest company in the world, made their thing by string matching. Okay, you press any stupid phrase in the world, they're going to give you every one of the billion web pages that have it. Okay, but it goes a lot more than just computers and things like that. There's a lot of work in this done with genetics and biology now, because basically they search through the genome. They're searching for different patterns of different types. Okay, and they're doing that. But that's genetics, but there's also medicine. Okay, it goes as follows. Cancerous cells or bad cells have certain hooks on it, that T cells, whatever, that connect to other cells. It's not hard to cure any disease. You just have to find those bad cells. You have to search through those bad cells. You have to find how to connect to those bad cells and then inject some poison into those cells. So it basically like that. Obviously I'm simplifying things because I don't understand things, but that's basically what this is all about. So what we're going to do is we're going to look through a few small algorithms just to show how string matching goes. And again, it's a whole world and it's worthy of looking into. Okay? So the idea is as follows. You're given a pattern. Pattern is the small one, of length m, and a text of length n, which is much greater than m. Okay? And your goal in life okay, we're going to write the pattern as P, we're going to write the text as T, and your goal in life, let's just, before we say your goal, J plus 1 all the way till K. This is the J through K pattern, characters of text. So this is the way we write. You have text, but you're looking at it from the J to the Kth character. You're not looking at all of them. Okay? Our goal is to find S such that P of 1 through M equals T of S plus 1, comma, S plus 2, comma, S plus M. That's what you're looking at. Our goal is to find the position where the pattern can be found within the text. That's exactly it. Okay, great. Okay, so the first thing we do is section 32.1, which is called a naive string matching algorithm. It's a silly little algorithm, but we want to go through it because we want to see what goes wrong, that we can do the more fancier algorithms. So let's go through it. Okay. So it's page 988. Now the algorithm is very readable. You can go read it on your own. But I want to do the following. P, the pattern is the word L-A-N-D. The text equals Alice in Wonderland by Lewis. I made everything lowercase just to make things a little bit easier. Lewis Carroll. Okay. Okay, great. So let's do it the way I would do it, naively. Okay. Okay. It goes as follows. I check L. Oh, sorry, don't want to do that. Hold on. Basically, what you're going to have to do is compare everything character by character. Compare every character from this one to every character from that one. Okay? So what you're going to do is compare L to the A. L to the A doesn't work. So the next thing you do is compare L to L. That works. We like that. Then you're going to compare okay. Then you're going to compare A to I. That doesn't work. And then you're going to what you're going to do then is you're going to have to move over. So you tried this one, it failed. But then you have to move over. Okay, so then you're going to try L, sorry, well, that was L to L, fine. Then you're going to have to compare L to I. Now notice you already did I already. You have to kind of go backwards and do it again. You don't like that. We don't like that. Anyways, L to I doesn't work out, L to C doesn't work out, L to E doesn't work out, L to E doesn't work out, L to I doesn't work out, Finally, you're going to get L to L. That works. Then you're going to go L to A. That works. Then you're going to go N to N. That works. And D to D. That works. Okay? So that's the way you do it. You do it basically point by point, but as soon as the first character matches up, then you try the second character, then you try the third character, then you try the fourth character. Great. This is a silly example because we don't have a lot of repetition. I want to show you what is a much more interesting example of this naive algorithm, and there you'll see more clearly what the problem is. Oops. Okay. The more interesting example is as follows. The pattern is equal to A, 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 B. The text is equal to A, 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 B. Okay. This is obviously not typical. I mean, you're not going to search for this phrase in Google, but we can see how the algorithm works a little bit more better and see what the problem is. Okay, I'm going to match A to A, that's good. I should use another color. A to A, that's good. A to B, the A to A, that's good. B to A, bzzzt, it fails. Okay, now watch what happens. Then, so I did 4 comparisons, then I'm going to have to continue like this. A to A, A to A, A to A, B to A. Buzz. Then I continue, but with this A. A, buzz. Then I continue with this A. In other words, I'm not continually going here. I'm going like this. compared to this one, compared to this one, it failed. Then we went back, compared to this one, compared to this one, compared to this one, failed. Go back, compared to this one, compared to this one, compared to this one, failed. Go back, da 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 da. Okay? And the main point is all the times I'm going back and going back and going back. What we're going to see later on is an algorithm where you don't have to go back. Now that's very interesting. Let me show you why. Because this algorithm, how long will it take in order to at last find A, well, let's go through it. Basically, I have to start at every single node. Okay, so what did we say? This is M, is the pattern. The length of M is the pattern. The length of T is N. I think I could be wrong there. T is N, right? Okay. So basically, I have to go through every single node of the text, and in order to do this algorithm, it would be M times N. Now, that's fine, okay? But I'd like to show you a better algorithm that takes M. Okay, that just takes, I'm sorry, a better algorithm that just takes N time, not M times N time. Okay, so we want a better algorithm that just goes through it very quickly. And we'll see that later on. Okay, so that's section 32.1. Again, it's the naive algorithm. Let me just tell you what we're skipping. Section 32.2 is called the Rabin-Karp algorithm. It's a nice algorithm, but it's a little bit mathy, and it really doesn't apply very well. Okay, it was one of the first algorithms, and it's clever, it's intelligent, but it's a math trick which doesn't really apply that much. Okay, so we skip it, and we come to section 32.3, which is called string matching with finite automatons. So I have to tell you what finite automatons. We're going to have like a half hour going through what a finite automaton is, and then we're going to do string matching with finite automatons. Let me erase the board. Okay. So we're up to section 32.3 called string matching with finite automatons. So I want to tell you what a finite automaton is. Finite automaton is a very weak computer. Okay? It's a very weak computer. It doesn't have memory. The only thing it can do is determine if some string is in a language or not in a language, a special type of language. Let me explain to you what I mean. Let me give you an example. A soda machine is a finite automaton. It's a very weak computer, and it understands, let's say a soda costs 35 cents. It understands the language of 35 cents. It understands how you make up 35 cents. Nickels, quarters, dimes, what's the language that makes up 35 cents? Okay? Anyways, again, a finite automaton helps you find a certain string, or lets you find a certain string. So let's do what a soda machine is. Let's think of a soda machine as a computer. Okay? You start off, you walk over to the soda machine has no money in it. Okay? It says 0 on it. That's its state. Okay? If you put a nickel in, then you go into state number 5, and it says on it 5. In other words, that's what you put in. If you put in another nickel, you go to state number 10. Okay, but you could do something else also. You can put in a dime right away. Start off at 0 and put in a dime. Let's go on. You can put in another nickel and you get to 15. You put in another nickel and you get to 20. You put in another nickel and you get to 25. You put in another nickel and you get to 30. You put in another nickel and you get to 35. Okay? And you can get to another state which returns money, and we're going to be a little bit sloppy about this. But you can also go from 10 to 20 and put in a dime. You also can put in a nickel and then a dime and get 15. Then you can put in another dime and you can get from 15 to 25. You can get from 20 to 30 with a dime. and get to 25 to 35 with a dime. Now here's the point. Anybody who gets here or here, and we'll talk about what that is later, they two circles. That means the word, the string of letters that you just described was accepted. Okay? The two circles means it's an accepting state, and it was accepted. It was permitted, which means you get the soda. Okay? But there's another letter that you can have also. You can start off at 0, and you can put in a quarter. Quarter's 25 cents. Damn. Or you could start off at 5 cents and put in a quarter, and you get to 30. Or you could start off at 10 cents and then put in a quarter, and you get to 35 cents. Okay? And you can be in 30 cents, put in a quarter, put in a dime, and get to 40 cents. And 40 cents you get the soda, but you also get 5 cents back. Okay, I'm going to stop going on with this. But the main point is, given a string, you can tell if that string contains 35 cents. Okay, so let's do it. If I put in nickel, nickel, dime, nickel, question, can I get my soda? And the answer is follow. So you start here, nickel, nickel, dime, nickel, 25 cents, not in the language. It's not in the language. Okay? How about this? Dime, nickel, quarter. Well, let's just do it. Dime, nickel, quarter will be something like this, going to a higher state. And the answer is yes, that is in the language. So that's in the language of 35 cents. Okay? So again, basically a finite automaton, what it does is it recognizes a simple language. A soda machine is a machine that recognizes the language of 35 cents. Okay? We're going to use finite automatons to find certain strings in a pattern, and it's going to help us very much. Okay? Okay, great. Let's be formal about a definition of a finite automaton, and then we'll see one more example. I'm going to erase this. Formal definition. A finite automata, it's actually automaton. Auto by itself, it works by itself. Maton. That's singular. That's a single. M. That's the name of a machine. Is a 5-tuple. Okay. Q0, A, sigma, and delta. Okay. Now I got to tell you what each one of these things are. So let's do it. Q is a finite set of states. Okay. Q0, member of Q, is a starting state. A subset of Q is a set of accepting states. I'll explain this all in a second. Okay. Sigma is an alphabet. And finally, delta, okay, delta is the transition function. It's the transition function. It shows you how you transition from one state to the other state. I'll show the hard part is that, okay? But the main point is Q is a finite set of states. Q0, one of those states is the starting state, okay? The finite set of states we drew with circles. Q0 was one of them, which we called, we put a little arrow there, that's the starting states, that's where you start. With the soda machine, you started at 0, okay? A is a few states, could be 1, could be 2, could be 3, could be none. It's a subset of states which we circle twice. Those are the accepting states, which means if you land in there, then that word is what you wanted. Okay? And finally, sigma is an alphabet. It's the letters that we had. For the soda machine, the alphabet was nickels, dimes, quarters. Okay? But we're going to have more interesting things. And finally, the transition functions. The transition functions tell you how you go from one state to the other. So let me be a little bit more exact. The transition functions are the programs. That's what this all is. This is a program. I told you a finite automaton is a very weak computer. Well, a weak computer also has a program, and that's what a finite automaton is. So the transition function is a function. It takes a state and a letter of the alphabet and tells you what other state to go into. Let me give you an example. If you're in state Q3 and you see the letter B, I want you to go into state Q21. That's a typical example. So we draw that as follows. This is Q3. This is Q21. And if you see the letter B, I want you to go from here to there. Okay, that's the way we draw this thing. Okay, so this is an exact definition of what a finite automaton is. Okay, let me just sell it for a second. Finite automatons are used all over. In particular, compiler theory. What's compilers all about? Well, you better be able to detect certain strings when a programmer is typing in a program. Okay? But it's also in theoretical computer science. It shows up all over. It shows up in linguistics because it's talking about language. Okay? It shows up all over, and it's a very important thing. And it's talked about in a lot of different classes. Let's do one example, which doesn't really have to do with searching for strings, which is the chapter that we're in, but it is a nice example and something you should see at least once. Okay? Okay, so let's talk about this example. The alphabet is made out of zeros and ones. Okay? Okay? And the language is the set of words in 0 and 1s, but I want specific words. I want those W words such that W has an odd number of zeros and an odd number of ones. Okay. This is called a parity checker. The number of zeros, the number of ones could be odd or even. Each one of them could be odd or even. Okay, so we have to make a finite automaton that does it. Okay, and I'm going to show you how it works. This finite automaton is going to have 4 different states. Okay. And let me show you how this works. There's a 0 here, there's a 0 here, and there's a 1 here, there's a 1 there. There's a 0 here, there's a 1 there, 0 there. Okay. Now, I didn't give these things names, but I'm going to give them, instead of giving them names, Q0, Q1, Q2, Q3, this clearly is the starting state. I'm going to give it as follows. Even 0, even 1. This is odd 0, even 1. This is even 0, odd 1. And this is odd 0, odd 1. Okay? And this is the transition function. So, I'd like to try a few words. Let's try a few words. 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0. 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1. And 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0. Okay, here's 3 different words. Let's see if the words are in there. We do it with our fingers. We follow the words with our fingers. You're going to have to see this both ways. Okay, let's start. You ready? We start here. Even number of zeros and even number of ones. The empty word, 0 zeros and 0 ones, they're both even. Okay, but then we do as follows. 0, 0, 0, 1, 1, 0, 0, oh, I'm sorry, 1, 0, 1, 1, 0. I end up here. That is not doubly circled. Conclusion, this word is not in the language. Okay, let's try this one. Ready? I'm going to go a little bit quicker. 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1. Okay, so it ends up here. It's not in the language. Let's try this one. You ready? 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0. Not in the language. Okay? But if I put on a 0 and a 1, it would be in the language. 0, 1, it would be in the language. Okay? So this is a parity checker. It checks that there are an odd number of zeros and an odd number of ones. If I wanted an even number of zeros and an odd number of ones, I would have circled that. Very nice. Okay? Now I want to do something closer to what is needed. Sorry, I want to do what's needed for string matching. Okay? And you'll see this in a second. Okay. Key point. Notice when I was going through here to not a key point. Let's not talk about that. Never mind. We're going to do like 1, 2, 3 examples, and we'll go back to some theory. So here's an example. I have the alphabet is equal to A, comma, B, okay? And I want the language, and I want to make a finite automaton that accepts this language, is equal to those texts such that T contains A, B, B, A, A. Okay? Anything that contains A, B, B, A, A, B, B, A, I want to accept those words. Okay? So I want to show you how you write such a thing. Okay? They're finite automatons, but they're straight, I call them snakes, straight across. Nothing like we had before with the parity. Okay? Okay, it goes like this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Okay. And basically, you write along the spine of the snake, you write what you want to get. So A, B, B, A, A. Okay? Now, next point. Once you have this word, this is an accepting state, means if you have A, B, B, A, that you've accepted, okay? And once you're there, you stay there. No matter what you get, you found what you're looking for, stay right there. Okay, great. Now I'm going to give these states names in a second. Well, let me give this names. Right now, I have nothing. If I'm in this state, that means I saw an A. I just saw an A. That's where I got that. If I'm in this state, I just saw an AB. You know what? I'm sorry, it should be in a different color. We'll fix it in a second. Of nothing. I just saw an A. I just saw an AB. I just saw an ABB. I just saw an ABBA. And here I saw exactly the whole phrase. ABBA. Okay? Those are the names of my states. I'm not sure the book does this. This is an extra nice thing that I saw in a different book, and I wanted to do that. Okay, great. Now, remember, that's not a finite automaton. Remember the definition of a finite automaton. We have the states, we have the accepting states, we have the starting state, but remember the transition function. The transition function says, you tell me what state, you tell me what letter in the alphabet, I'll tell you what state. I need to know for every letter, these are pairs, state, letter in the alphabet. I need to know for every letter and every for every state and every letter what to do. So question, what do I do if I'm here and I see an A, I go here. But what if I'm here and I see a B? And the answer is I go here. Okay? Now this is the hard part, because we're going to do it for all of them. And this is the core of it. Ready? I'm here. If I see an A, if I see a B, I go here. That makes sense. But what happens if I see an A? Now, the main point is I do not go back here, because if you see an A, then the last thing you see will be an A. So you stay right there. Okay. Again, being in this state means that the last thing you saw of this pattern was an A. Okay, great. Let's do this. Now, in this state, I have something to going out A and B. That's good. In this state, I have something going out A and B. Good. In this state, I know what to do if I see a B. What happens if I see an A over here? Okay. What happens if I see an A over here? If I see an A, I don't stay here, because then the last thing I would see is AB. No, the last thing I saw was an A. Well, AB. The last thing I saw was an A. If I see an A from here, I go back here. And I wait for another B. Okay? Let's just see. What I got here, you got A, B, A. No, I need A, B, B. So I have to go back here. This is where I wait to see an A. This is where I wait to see the rest of the pattern. Great, I am here now. If I see an A, I go here, and I listen to great music, ABBA. But if I'm here, where should I go? Now let's go back to, this is a key point. If I'm here and I see a B, where should I go? That means the last thing I saw was a B. Okay, actually I saw A, B, B, B. What should I do? Answer, I have to go all the way back to the beginning and wait for my pattern again. Okay, I don't go here because the last thing I saw was a B. That's for that. I don't go here because the last two things I saw was not an A, B. It was A, B, B, B. Not A, B. So I don't go here. I go back to nothing, which means I have not seen any part of this pattern yet. Let's go here. If I have an A, B, B, A. If I see an A, I go in here and I say, yippee, I found the pattern. But if I am here and I see a B, where should I go? Okay. The last two things I saw was A, B. Okay. The last two things I saw was A, B. Okay. Again, I'm here. The last two things that I saw was A, B. Okay, and so I go here. Okay, watch. A, B gives me A, B. Okay, now I want to show you why this is a great way to search for things. Watch this. 1, 2, 3, 4. Okay? Okay. I want you to keep an eye on this finger. I want you to keep an eye on this finger because I'm going to go, this finger is going to go, I'm sorry, I want you to keep an eye, sorry, okay? I want you to keep an eye on this finger because that's what I'm going to do. I'm going to follow here. You ready? I'm going to start here with the empty word, B, A, B, B, it's going good, B, A, B, B, A, B, B, I think I'm here, A, A, and I got it right here. That's the word, A, B, B, A, A. The main point is this finger just continued going straight. That's the main point. I continued going straight. I didn't back up one bit, which means, and we're going to say this over and over again, once I have this finite automaton, I can continually read this formula straight across, which means that this algorithm to find this thing will be the length of the text. That's very cool. That's very, very cool. Okay? That's very, very cool. I'll tell you why it's very, very cool. Because I can't say a pattern, I can't get better than the length of the pattern. The idea is as follows. You want to know if a certain pattern is in the text? Well, you have to search through the text exactly once, just the length of the text. Okay? Not the length of the text times anything, just the length of the text. Okay? Again, do this again and you'll see as you're bouncing around, pick another string and text. As you're bouncing along, you only go forward here. The arrows are telling you how much back in the pattern you should go. But not but this finger always went straight forward. Okay? Which means the algorithm is O of n. Okay? Let's do another example. Okay? The examples are all exactly the same, but I mean similar, but we get experience doing them. Okay. Let's go through it. The alphabet is X, Y, Z. By the way, I don't do the example the book does, so you get to see that by itself. T contains Z, Y, Z, 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 X. Okay, let's start. We're going to put along the spine, we're going to put the pattern. Obviously the finite automaton depends only on one thing, the pattern. Z, Y, Z, 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 X. 3 Z's and an X. That's our accepting state. We're happy. If we get to here, we're happy. And no matter what you see, you stay here. X, Y, let's make it capital, Z. Okay, I just want to put in before the names of the states. This state, I saw nothing. This state, I saw Z. This state, I saw Z, Y. This state, I saw Z, Y, Z. This state I saw Z, Y, Z, Z. This state I saw Z, Y, Z, Z, Z. This state I saw Z, Y, Z, 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 X. Okay? That's the easy part. That's the same for all things. The question is about going back. That's always the hard part. But we're going to do it. Ready? Let's do it. I'm going to do it without looking at my paper. If I see a Z, I go here. If I see an X, I just wait. If I see a Y, I just wait. Don't go anywhere. Great. Now, if I'm here, I just saw a Z. If I see a Y, I go here. If I see an X, I go here, because there's only X's back there. It's the end of the thing. If I see a Z, I stay here. Okay, great. Now I'm here. I just saw a ZY. If I see a Z, I go here. If I see an X, I go to the beginning. Because, okay. If I see a Y, I think I also go to the beginning. Because ZYY is not the beginning of anything. So we'll do that as a Y. Okay. Sorry, let's check that, make sure that's true. XY. Good. Okay, let's go here. I just saw a ZYZ. If I see an X, I go to the beginning. Okay. If I see a Y, then look what I just saw. If I'm here, I saw a ZYZ, and now I see a Y. So then I go right over here, because the last two things I saw was ZY. Okay. The last two things I saw was ZY. Great. Next. Okay. Next. I just saw ZYZZ. Again, if I see an X, go back to the beginning. X is not helpful here. If I see a Z, I go here. That's better. But if I just saw a Y, ZY, then I think I go back here. Let me just make sure. Yeah, I think so. zy, I go back here. Okay. Same thing here. If I see an x, great. If I see a z, let's do y. If I see a y, then the last two things I saw was zy. So that goes here. Okay. If I see an x. Okay. What happens if I'm here? I saw zy, z, 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 and I see another z. Okay. Well, I'm not looking for zy, zz, I'm looking for z here. And so this goes to here. And I'm finished. Okay? But now we're going to do a nice word. And again, what you're going to see is my finger going across here very nicely. X, Y, Z, Z, Y, Z, Z, Y, Z, Y, Z, Z, X, 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 Y, Z, 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 Y. Okay, let's follow. Okay, this finger is going to keep on going. Let's do it. X, Y, Z, Z, Y, just so ZY, okay, Z, Z, Y, Z, Y. Notice this finger goes back, but this continues to go forward. Z, Z, X, all the way back to the beginning. X, 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 stay there. Y, stay there. Z, 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 Y. I end up here. Okay? So this word is not in the language. This text does not contain this pattern because I ended it up here. It's very nice. Main point, I kept on going forward here. I went backwards in the pattern looking for things closer to the thing, but I didn't find it. Okay, good. Let's do one more example like this. And this is going to be a lot of repetition. We're going to like this example. Let's just erase this. Erase this. Again, the book has examples. You have to read the book yourself. It's very clear. It's very clear. This is very straightforward. It's a new concept. This finite automaton is a new concept, but once you see what it's made out of, why it's done, it makes sense. Okay? I don't know when I made these examples up, but they're made to be. Okay? Things get interesting when there's a lot of repetition in the examples. So we're looking for text such that the text contains M, M, P, M, M, A. I did this specifically because you're going to get confused with the first MMs and the second MMs, but it's going to be good. So let's do it. One, two, three, 4, 5, 6, 7. Okay, I'm going to write 7. Okay, so let's put in the phrase. This is the starting thing, so it's going to be M, M, P, M, M, A. Okay, once I get in here, whatever you see, you stay. So M, comma A, comma P, comma Q. Rather than making 4 different arrows, I'm just going to write one arrow and say like that. Great. Okay. Now, can I make a suggestion? Before I make a suggestion, let's fill in the last thing, what we saw. Okay, so let's fill this in. Here I saw nothing. Here I saw M. Here I saw MM. Here I saw MMP. Here I saw MMPM. Here I saw MMP, MM. And here I saw MMP, MMA. Okay, great. Okay. This gets doubly circled because this is the accepting state. Okay. Can I make a suggestion? You stop right now, fill in the rest of the arrows. Pause the stupid button, pause the YouTube video, stop it, and fill in the rest as a nice test for yourself. Okay? I'm assuming you did that, and we're going to go forward and do it ourselves. Okay? If you're here and you see, I'm going to be a little bit quickly, an A, P, or Q, you go here. A, P, or Q, you go back to the beginning. Because you need an MM. You need to start with an MM. Okay, if you're here, and you see an M, this is interesting. If you're here and you see an M, so the last thing you saw was M, okay, and M. The last thing you saw was MM, so if you see another M, you stay right there. Okay, now you just wait there until you see a P. Okay, but if you see a P or a Q, an A or a Q, if you see a P, you go this way. Okay, so that takes care of that. Next, I just saw MMP. If I saw an M, I go here. If I see an A, I go all the way back to the beginning. That's no problem. If I see a if I see a P, then the last thing I saw was PP. PP is not in my thing, so a P goes here. And if I see a Q, also I go there. Okay, that takes care of that. Next, I'm here. I saw MMPM. If I see another M, I go here. That's good. If I see an A, it's all APQ. APQ. Okay. This is slightly more interesting. If I see MMPMM, okay? If I see an A, I go here. That's great because that's what I'm looking for. If I, by the way, anytime I see a Q, I have to go all the way to the beginning because Q is not in my thing. Q is not in my pattern. So anytime you see a Q, you automatically go here because start over. It's not in your pattern. But let's do this. Here's where it gets more interesting. Let's say you see an A, you go here. Let's say you see a P. Where should you go? You just saw MM, and now you see a P. Where should you go? Answer: you should go right over there, because that just says I just saw MMP. MMP. That's where I belong. Okay. So Q goes there. A goes there. What happens if you see an M? Okay. So, let's just see. The last three letters you saw were MM. Now you see another M. Where should you go? And the answer is you should go right over here. You just saw two M's right over there. Wait again for the beginning of your pattern. That takes care of everything. If you have to understand this one, all the arrows, the three different arrows that it comes out of. Okay, I did this example so I can do this arrow, this one. Okay, let's just do an example. And again, the main purpose of this example is to see that my finger continues to go forward. M, M, A, M, Q, M, Q. Every time I see a Q, I'm automatically going to the beginning. M, M, P, M, 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 A, P, Q. Tell you right now, I'm going to be there. M, 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 P, M. Okay, so here's a nice word. I'd like to know if this word is in my language, if this text is there, so let's follow it. You ready? M, M, A, M, Q, M, Q, M, M, P, M, M. So M, M, P, M, M, I'm here. Then I see another M, I'm there. Then I see an A, here. Then I see a P. Hey, we didn't do this. This is, you see an A, a P, or a Q. You stay right there. Anyways, this thing is not in the language. Okay? Main point, I was going forward the entire time. Okay. Let's do a little theory. Now that we had 3 nice examples, we can do a little theory. Okay, and it goes as follows. You have a final state function. Okay, following the book's notation. Phi says, you give me a word that's a word of length n. I don't care how big the word is. And I'm going to tell you what state you end up in. Okay? Phi is a function. It takes a word. You always start reading the word at the beginning of, at the initial state of your finite automaton. Tell me what state I end up in. Okay? Let me show you how phi is defined. It's defined recursively. We love recursion. Okay? Phi of epsilon, that's the empty word, okay, is equal to Q0. That's your boundary condition. Start off your recursion at Q0. Start off your state at Q0. Next, phi, you give me a word with a letter A followed by it. Okay? So this is a recursion. This is words. So I'm saying, you want to build up your word? You have a word followed by a letter. Let me tell you what it's equal to. This is equal to delta, that's your transition function, of phi of W. Tell me where your word ends off after phi, then do the letter. This is some state. This is a state. Okay? That's the output of this word. Then do a letter. Okay? So then do the transition. So let me just do an example. You have a 12-letter word. Okay? A 12-letter word followed by A. What state does it go to? Answer. Look at where it goes to after doing its 12 letters. That's some state. You're going to end up in some state of the finite automaton. Then follow the transition function. If you're in this state and you see the letter, what's the other state you're going to do? Okay? So this is an induction. This is like saying how you go from n to n plus 1. We know induction. We know recursion. We've done this many times. Okay. Okay, great. Okay, now, the main point, okay, the book goes through a little discussion of this, very important, very nice. You're going to read it on your own. The main point is as follows. The main point is a point about analysis of algorithms. Okay, the main point is as follows. How, given a text of size n, so the text of size n, how long does it take for you to find the element in the thing? And the answer is O of n. It takes O of n to find the pattern, because all you have to do is go through the text, one letter at a time. And notice you can't go any quicker because you have to look at every single letter. So you can't go, not being exactly there. But that's O of n. Before, the naive example had n times m. Okay, this is O of n, that's much better. But there's some extra work. There's some extra work. Why? Because you have to generate that finite automaton. You have to make that finite automaton. So, to make the finite automaton, okay, how much work does that take? Let's think about it. Your finite automaton has how many states? Well, it depends on how long your pattern is, right? That snake has a certain thing. So you're going to have to deal basically, m, small m, okay? To make the finite automaton, how much work has to be done? Well, m, the number of patterns, and then think what you have to do for each one of those states. You have to calculate where the arrow for the letter should be. Okay, so it's times the number of elements in the alphabet. Okay, because for every state and for every arrow, you have to determine which place you should go to. That's exactly what's going on. Okay, so when I press Control F, I have a giant web page. I want to search for a certain phrase. I press Control F. What the computer, I type in the pattern. What the computer then does is make that finite automaton. It creates that finite automaton. Once it creates that finite automaton, you can go ahead and you can find the element very quickly. Okay? This is called pre-processing. We're not doing it while we're doing the algorithm. We do it beforehand. Then you press Control F, you make that finite automaton, then you can do it on any text whatsoever, as big as you want, and it's going to go fairly quickly. Okay? Let me just, okay, the main point is you don't have to go back. On the algorithm, there's an algorithm that shows how this works. It's on page 999. You have to understand that algorithm. I'm not going to write it because it's only 5 lines, but basically it uses the finite automaton to go further and further looking. It's called Finite Automaton Matcher. It's on page 999. You are responsible for it. Okay? And that's the end of string matching. There are a few other string matching algorithms that are done in the chapter that go more quickly. They show you how to do things even quicker, and they show you how to make the finite automaton even quicker. Okay, so that's a hard thing also. This pre-processing of the finite automaton is also a hard thing. Great. I'm probably not going to teach any other section. Obviously, this video is for any semester whatsoever, so I don't know. But if this is the last thing, what I want you to gain from this class is as follows: that whenever you have a problem, programming or thinking or designing an algorithm, if you spend time thinking about it, if you spend time thinking about the tricks you learned here, you're going to make a much better algorithm. It's going to be a much more efficient algorithm. It's going to be better not only in time, because time efficiency is not really, computers are so fast, but you can think of better ways of making that algorithm better for the user, better for the company, whatever, etc., etc. Anyways, I just want to praise analysis of algorithm. It is a beautiful subject. It is an absolutely beautiful subject that anybody can make a contribution to, because there are always new problems that computer scientists are trying to get to. So you can always come up with a newer algorithm, better algorithm, and you think of the problems and you can get great stuff. I hope you enjoyed the class. It's been a pleasure teaching you. Take care.